Alright, so let us begin our discussion of integral calculus. So basically, integral calculus, the subject matter is the opposite of differentiation to start with. Of course, as we see eventually, we figure out how to calculate areas bounded by curves, which is sort of the more interesting goal. I mean, just doing the opposite of derivative in and of itself, I suppose, isn't too interesting, but here's our starting point anyway. If f prime of x, big F prime of x, is equal to little f of x for all x in the domain of little f, then the big F is called an antiderivative of f. I say it's an antiderivative because, of course, there are many, right? In particular, we have this theorem. If big F prime is equal to big G prime for all x in some connected subset of the reals, then f of x is equal to g of x plus c for some real number c. So it's kind of embarrassing. There's not just one antiderivative. Because this c is totally arbitrary. If there's one, there's infinitely many. My goodness, it's a lot of them. So a corollary to that, of course, is just this. Any two antiderivatives of f of x are related in a simple way. If the domain of f is connected, and f and g are antiderivatives, then f of x is equal to g of x plus some constant. So for that reason, it's convenient to introduce some terminology, in particular the so-called indefinite integral. The indefinite integral of f of x, technically speaking, we should think of it as a set of functions. It's the set of all possible antiderivatives for the given integrand, little f. In other words, all big F such that big F prime is equal to little f for all x in the domain of f. All right. So, but I put quotes over here because you're like, I don't remember writing sets of functions in Calculus 1. Well, you probably didn't. And I wouldn't be terribly surprised if your instructor never told you this. I would guess it's probably not widely agreed on. Probably most people don't. I don't know. Who cares what people think? Anyway, this is, I think, what you should think. Different people can think what they want. I can't make people think anything they don't want to. Anyway, here, so f is the integrand. So you don't want to really write, well, here's an example. The integral of x dx, right, is what? Well, it is, get rid of this paper, a lot of things. It's 1/2 x squared. That's an antiderivative, right? 1/2 x squared plus 3, also an antiderivative. 1/2 x squared minus pi, also an antiderivative. And we could go on like this a long, long time. In fact, 1/2 x squared plus c, where c is any real number, all of these are antiderivatives of that. So the set of all of them is what I think of when I think of the indefinite integral. But of course, sets of things are kind of a drag. So instead of writing set like this, it's custom just to write 1/2 x squared plus c. The reason you must write plus c is because it's not a specific function. In fact, it's the class of all functions which, when differentiated, give you back the integrand. All right. Technically speaking, it's an equivalence class of functions, where the equivalence is measured by whether or not the two functions are related by simple translation of the output. Right. So, like, graphically, right? Graphically, it's pretty simple. How are these different antiderivatives related? Just by translation, right? So, all these different antiderivatives I have here, they're just, if I could graph, this is supposed to be the same shape. If we could go on and on, I mean, this is just, here's c equals to 0, here's c equals to 1, here's, maybe that's c equals to minus pi, I don't know, and so forth and so on. Any point you pick in the plane, right? Any point at all that you pick in the plane, there is one of these antiderivatives which goes through, right? The graph of it. So that's significant, right? As we'll see as we soon study the so-called initial value problem. All right, so there's your basic example. I won't talk about sets of functions after this point. I'm just saying, for the sake of calling a you know, calling it what it is. Okay, so now our next order of business, of course, is how do you calculate antiderivatives, or, well, really more to the point, how do you calculate indefinite integrals? Of course, after the indefinite integral, we'll study definite integrals, but definite integrals are numbers, indefinite integrals are classes of functions. So let's do some indefinite integration, which I tend to just call integration, right? A good portion of Calculus 2 is spent, I don't know, maybe 20% of it was spent on techniques of integration, all right? All right, so basically the story is this. For every derivative, right, there's a corresponding antiderivative. So, for example, integral of x to the n dx. What is that? Well, that's x to the n plus 1 over n plus 1 plus a constant, right? Why is that? Because if we differentiate with respect to x, x to the n plus 1 over n plus 1, what do we get? Well, we get 1 over n plus 1 times n plus 1 times x to the n plus 1 minus 1, right? Oh, I dropped the constant. The constant differentiates to 0, right? So I won't even bother writing that. And so what do you got? Well, these cancel, right? And you get x to the n. And there you have it. That proves that this formula is indeed legitimate. Now there's some important fine print here, right? N not equal to minus 1. We do need to know that. So, all right. Now, little comment, what about n equals minus 1? Well, I should tell you a little story. Check this out. The derivative with respect to x of the natural log of the absolute value of x, what's that equal to? Well, that is d dx, right? Of the natural log of the square root of x squared. All right? So that is d dx of 1/2 natural log of x squared. So then by the chain rule, I get 1/2 1 over x squared times 2x. In other words, x over x squared, also known as 1 over x. So, usually we write this. The integral of dx over x, right, is equal to the natural log of the absolute value of x plus a constant. Now, I guess to be fair, there's kind of a little bit of a cheat here, because maybe what we really should say is the integral of dx over x is equal to, well, it's equal to the natural log of minus x plus c1, where x is less than 0, or it's equal to the natural log of x plus c2, where x is greater than 0. But this doesn't usually come up too much, because almost always we're looking at something, positive subset or a negative subset of real numbers. So we can usually get away with this sleight of hand right here, and we'll do the same. So the integral of dx over x, or 1 over x, is simply the natural log of the absolute value of x. The absolute value there, of course, is important, because when x is negative, there is still an antiderivative for 1 over x, but it's not natural log of x anymore, because natural log of a negative number is not defined. All right. So just a couple examples before I get off the topic here. Let's see, example 1. Oh, I guess it's 2. Example 2, how about the integral of the square root of x dx? All right, so this is x to the 1/2 dx, so I do x to the 1/2 plus 1, which is 3/2, divided by 3/2, plus a constant, aka 2/3, x to the 3/2, plus a constant. All right, there's one. How about the integral of dx over x squared? guess this is example 3. So that's the integral of x to the minus 2. Alright, so that's the x to the minus 2 plus 1 over, well, minus 2 plus 1 is minus 1, right? Also known as minus 1 over x plus a constant. Alright, we could go on like this. Here, I'll do one with a little bit of algebra. The integral of x squared plus x over the cube root of x. It's supposed to be a 3. Dx is what? Alright, well, let's see here. So that's the integral of x to the, let's see, 2 minus 1/3. Let's see, that's what, 6? 6 thirds minus 1/3 is 5 thirds. And then, let's see here, 1 minus 1/3 is 2 thirds, right? Like so. And given the pattern we just saw up there a second ago, right? The pattern we saw up here. By the way, the integral is additive. The integral of the sum is the sum of the integrals. So that's kind of nice, all right? So if I add 1, I get 8 thirds. So that's going to give me 3/8 x to the 8 thirds plus, let's see, 2 thirds plus 1 is 2 plus 3 thirds, which is 5 thirds. So I get 3/5 x to the 5 thirds plus a constant. And there you have it. All right, so there's a couple basic antiderivatives. We should be able to do these in our sleep at this point, I think. All right. All right. So there's some basic integrals. Let's keep doing this. All right. So let me just shout out for some properties. What are some properties of the indefinite integral? The main ones are this: the integral of f plus g, right, is equal to the integral of f plus the integral of g, like that. And also the integral of a constant times a function is equal to constant times the integral of the function, right? That's about it in terms of the basic things. The integral of f times g dx is certainly not equal to the integral of f dx, integral of g dx. This is just not, oops, I forgot to, oh, stink. Let me just scratch that one out. I mean, the integral of a product is not the product of the integrals. It's just not, it doesn't work that way, all right? For example, the integral of x squared, x times x, right, is the integral versus the integral of x dx times the integral of x dx. Well, what's the difference? Here we have x squared, right? So that's what? That's 1/3 x cubed, right? Plus a constant versus 1/2 x squared plus a constant times 1/2 x squared plus another constant. It's pretty obvious that, right, this and that are not the same. So do not do this. It is not true. All right. So further antiderivatives, and I should say integrals. The integral of, I'm just going to rattle them off at this point. Integral of e to the x dx is equal to e to the x plus a constant, right? The integral of sine of x dx is equal to minus cosine of x plus a constant. The integral of cosine of x dx is equal to sine of x plus a constant. All of these are easily checked by the fact that if you differentiate the integral, right, you get back to what? You get back to the integrand. You can always check our answer that way. Derivative of e to the x is e to the x. The derivative of cosine is minus sine, but minus a minus gives me plus. Derivative of sine is cosine. what else do we got? The integral of sinh of x dx is cosh of x plus a constant. The integral of cosh of x dx is sinh of x. Notice the lack of a sign here, sign, like that. Let's see here. What else can we say in terms of basic integrals? How about we also know we know that the integral of secant squared x dx, right, is equal to tangent of x plus a constant, because we know that the derivative of tangent is secant squared. Let's see here, what else do we know? We know that the integral of secant tangent is equal to secant of x plus a constant. We know, let's see, what else do we know? The integral of cosecant squared x dx is equal to minus cotangent x plus a constant, right? And we, of course, also know that the integral of cosecant cotangent is equal to, well, minus cosecant x plus a constant. So, I mean, all of these things we really should know just cold. Now, there's a couple of more things we should know. Let's see here, example 14, the integral of dx over x squared plus 1 inverse tangent, because the derivative inverse tangent is 1 over 1 plus x squared. Another thing we should know by memory, dx over the square root of 1 minus x squared is equal to inverse sine of x plus a constant. Let's see here. Let's see if I make sure I haven't missed any. Looking over my integral table. Anything else that's basic that we should just know? Let's see here. I think that's it. But these ones, we really, if you have to look these up, that's not good. These we should know without flinching. If you don't have these memorized already, you need to memorize them. Because the point of one of the things in Calculus 2 is if you get to something like one of these, you need to know, oh, that's the end of the line. I'm done. Already, that's the basic integral. End of story. All right. So there's a few more kind of like this that are a little bit less known, and I'll go on to those next. Thanks, guys.